So I'm Looi. I'll be talking about performance. I'm a senior PE. I've worked a lot on different parts of the Intel's platform, which comes in handy for working on this Intel DC persistent memory, which is ends up touching pretty much every piece of the platform. So I'm going to talk more about the module and the performance, and then break into the memory mode and how performance works with the modules, and then app direct mode. And in the app direct mode, I'll talk a little bit about workloads and how you can optimize your workload to take advantage of the persistence. Okay, so here's the basics on the module and the performance. So Mohammed talked a lot about different platforms and different requirements, and some customers can cool up to 18 watts or deliver power up to 18 watts, and some 15 or 14 or whatever. So the module is programmable from 12 to 18 watts in quarter watt granularity. So any of those are fine, and you can choose between power delivery and cooling and performance. Obviously, the higher the power, the better the performance. Now, the performance of the module varies a lot on the type of traffic it sees, and that's a little bit different than DRAM. So Mohammed mentioned that the interface to Optane is actually 256 bytes. And so if you have a contiguous 4 cache line 256 byte access, that gives you different performance than if you're just accessing single 64 byte cache lines. And we'll look at that in a second. The other thing that will vary is if you're doing reads or writes, the performance will be different on the module. And once you put it all together, I have an example here with a 256 byte 18 watt module. So up here, these are all the accesses and bandwidths with the 256 byte granularity. You can see that the bandwidths here are higher, with the highest being reads and the writes here. And then if you do a read-write mix, it's somewhere in between. In the bottom rows here, these are 64 byte accesses. And similarly, the read is a higher bandwidth than the writes, with the read-write mix being in between. So these are all the characteristics of the module, and they will affect the system performance. And once we get into memory mode and app direct, you'll see how that plays out.
So there was some question about, so SSDs have write amplification problems, right? Optane does not, but you're really accessing 64 bytes from the bus, but 256 bytes are being read and written.
Correct.
So how don't you do write amplification?
It's just smaller. It's 256 bytes, so it's smaller.
So you still are dealing with a block that's being written or read to the Optane media.
256 byte.
Yes.
Yes. And it's done with a read modify write.
Okay.
Okay.
Oh, you can read modify write though.
It's all on the module, and it's all handled by what Mohammed called the brain, so the controller.
Okay.
So one other comment here. This is all for one module. You can put up to 6 modules on a socket, and without any special software. So you can get the scaling similar to a DRAM. If you put 6 DRAM on, you get the best bandwidth. Same with these modules.
So you could end up with, for example, 5.4 times 6
right.
per processor.
Per processor.
Box.
Yep. Okay, so we looked at bandwidths. This is a similar chart, same example, 18 watt, 256 gig DIMMs. And the way to read this graph is going on the x-axis, this is the bandwidth. And if you look at the purple line there, that is the persistent memory module. And if you follow all the way out, the bandwidth goes out to just a little bit above 5 gigabytes per second, which was the same as the previous table. And that's the bandwidth. Now, on the y-axis is latency. And so you can see the latency starts on the left at the lowest point, about 180 nanoseconds. And as you increase the traffic, the latency will go up, but not until it's almost fully saturated. So that's the way to read this graph. Now, just for comparison, we have here the Intel Optane SSD, and then also a NAND SSD up at the top. And you can see going from the NAND SSD to, say, the Optane SSD, the latency is an order of magnitude better. And then going from the Optane SSD to the persistent memory is another order of magnitude better. So this is a huge latency savings, and I'll talk a little bit more where this latency savings is coming from. But that's...
So the read-idle latency, is that a DRAM?
No, well, the read-idle latency here, it's to the persistent memory module.
Okay.
It's about 180 nanoseconds. In comparison, DRAM is probably about 70 nanoseconds. And also in comparison, the DRAM bandwidth would go out quite a bit farther than that.
Does DRAM suffer sort of a hockey stick kind of solution as you drive it up bandwidth-wise?
Yeah. DRAM is the same. It's just that it would go out a little further. Maybe for a single DRAM DIMM, 18 gigabytes per second approximately. But this gives you an idea of the order of magnitude of performance compared to even an Optane drive.
I guess I also didn't realize that Optane had asynchronous or imbalanced read-write access. So you can actually read a lot faster than you can write.
That's true. That's correct. Okay, and just one comment. I didn't mention it, but these the drives, the SSDs, those are all on a 4K granularity. This graph here is 256 bytes, so you get a much better granularity. If we had done a 4K access, it would look the same. The purple line would be the same. Same picture, and I'm a little short on time, so I'll just buzz through it real quick. This is the same picture, added more data points. So the dotted lines are reads, whereas everything else was previously read-write mix. And I've also added in the 64-byte accesses, so you can see where that fits in. And again, the drives are all 4K.
And these are all at 18 watt.
These are all 18 watt, right? Okay, so let's dig into memory mode here. And before we go too far into memory mode, I wanted to talk through the transaction flow a little. Both Ian and Mohammed talked quite a bit about the memory controller. It plays a very central role in how memory mode works. So let's step through an example of the flow. And we can start with the picture in the middle. So this is what happens in memory mode when it's a hit into DRAM. So first, the CPU core issues a read, and the memory controller will route it directly to DRAM. When the data returns from DRAM, memory controller will actually look at the data and do a quick check to see if that data truly was a hit in the DRAM cache or if it needs to do anything else. In this case, it was a hit in the DRAM cache. The data is returned back to the CPU core, and your latency is about the same as it would have been for DRAM. On the right, this is a DRAM cache miss. So it starts the same. The CPU core sends a read. It goes to memory, comes back to the memory controller on the CPU, does a quick check, and it sees, oh, it's not a hit in DRAM. I need to go fetch it from the persistent memory module, or the far memory, as we call it. And so that's what it does. It goes and fetches far memory and then returns the data for the CPU to use. So in this case of a cache miss, your latency is going to be a combination of the DRAM latency plus the latency to go fetch it from the far memory, or the Optane persistent memory. Okay, with that basics, I want to talk a little bit about workloads, and then we'll get into some examples of workloads. For the performance varies by workload.
So the writes to cache or the write back, is that how this works?
Oh, for writes to the DRAM cache?
Yes.
So usually when you're writing something, you've already done a read for ownership sometime in the past. So the write would actually go to your L3 cache, and when the time is right, it would be evicted to the DRAM. Now, eventually, someday in the future, when that same DRAM space is needed for new data, then that would be written out to far memory.
So there's a D-stage process from DRAM cache to the Optane solution that happens at the time of cache full.
Eviction, yeah.
And that kind of thing.
Yep.
And that's
like
all done through the memory controller.
Yeah. So yeah, this was not just the module, but I mean, it was a full system change. So Another question?
Go ahead, I'm sorry.
Okay, so in terms of workloads and traits, just like any cache, good locality will give you a good cache hit rate, and that will give you good performance. So that's one important trait of workloads. Another way to think about that is Mohammed talked a little bit earlier about hot data and cold data. So if your hot data, the most actively accessed working set, is reasonably sized and can fit in memory, then you have good locality.
So your D-stage process and your reading process to DRAM are both going to affect DRAM bandwidth as well as potentially Optane. So Optane becomes a bottleneck. Optane writes become a bottleneck during a D-stage process.
A D-stage?
And the D-stage is driven by cache slot availability or DRAM cache slot availability.
I'm not sure what a D-stage is. What is that?
So the D-stage is from DRAM to the Optane, right?
Oh, okay, got it. Yeah, yes. So during the period where you may have a lot of evictions all at once, that would become the bottleneck, but usually it's more balanced system than that. And that's why when we look at workloads.
Yeah, okay.
Okay. The other thing to keep in mind, once we've got the whole cache and locality dialed in, is what is the actual bandwidth demand of a workload? So if the workload is demanding a moderate to low amount of bandwidth, it has different traits than if it's demanding the maximum bandwidth the system can support. Some other factors, and you could gather these from what we just looked at and the module characteristics, number of reads versus number of writes, that will also have an impact. And also the configuration, so the number of DRAM DIMMs, the number of persistent memory modules versus the actual workload size, they will also impact how it performs in a workload. And there is a link down here at the bottom that that gives you pointers to vTune to help analyze the size of a workload. But typically it's like your data set size plus a little bit of working space.
And again, it's this particular solution is better at reads than writes.
Yes.
Okay.
Okay, so these are some graphs that we generated running with a synthetic workload called MLC. It's actually available on software.intel.com. And with this synthetic workload, we were able to vary the demand of a workload, and we were also able to vary how much it hit in the DRAM cache or not. And this is to mimic what real workloads would do. So looking at the two blue bars, the dark and the light blue bar, those mimic a workload that has a light or a medium demand. The bottom line is 16 gigabytes per second, the top is 40 gigabytes per second. And then we varied the size of the buffer that we're accessing to force different miss rates.
And when you say the demand is 16 or 40 gigabytes per second, that's the demand between Optane and DRAM?
That's the application request rate. So sometimes
So the application
are computing.
request rate to level 3 cache and DRAM, is what you're saying?
Correct, yeah. Whatever the application wants to access. So in this case, as we varied the miss rate, because the request from the application was at the moderate or lower level, there was really no bandwidth degradation, even as you increase the miss rate. The yellow line, that would be mimicking an application that's asking for data at the highest possible rate, and at the left, when the DRAM miss rate is 0, so you're hitting a DRAM all the time, you basically get the same bandwidth as you would get from just running a DRAM system. And as the miss rate increases, you can see there is a degradation in the bandwidth. So that's something to keep in mind, looking at the type of application that's being run. So if you have an application that's constantly demanding the highest bandwidth and is randomly spraying all over the place without any locality to take advantage of the cache, you would see a degradation. So this kind of is a landscape of workloads with this, with
I noticed
memory
you
mode.
cut
And with
the graph off at 50% miss rate. Is it pretty flat from that point on?
More or less. Well, the yellow continues. to drop. But yeah, you're able to sustain a base bandwidth.
So I totally missed, probably somebody told it, but can I have a larger cache? So can I set up a very large cache?
So you can control the cache by how much DRAM you put in your system. So if you use bigger DRAM DIMMs, then you have a larger cache. And that is a good way to accommodate different sizes of workloads and workloads with different sizes of hot data.
Do you already have best practices depending on the workloads, or are we still in a...
A general rule of thumb is between 4 and 8 to 1 ratio between the far memory and the near memory. That's generally what we do. Sometimes we'll do 16 to 1 ratio.
So
we don't
are
have
you
a tape
publishing cache miss rates and stuff like that as part of your statistics or metrics so that people can understand whether they even have a problem or not?
We measure that. I don't know if we're publishing them, but we do.
So it's not something that you would be able to monitor on a server or something like that and say, oh, its miss rate is X amount.
You can, and anybody can monitor it using VTune or something like that. There is a statistic for miss rate.
For
the
DRAM memory mode Optane miss rate.
Yeah.
Yeah, for both the 2LM or memory mode as well as for AppDirect, we have performance monitors that allow you to identify pieces of code or parts of data that are actually experiencing those types of behaviors. So beyond being able to just identify, what's the overall behavior in the system, you can actually go in and say, this is the code that's doing it, or these are the data structures that are seeing different types of behavior. So those are also some capabilities that we've built into the hardware as well as our software like VTune and Linux Perf.
Yeah.
And you
earlier I had a link to VTune, which...
And you limited the number of Optane slots to 6. Is that a power issue, or?
It's just architecture, the way the architecture works. So 12 channels, and then one of them can be Optane. And then typically put DRAM on the other slot. Okay, so now we've got the basics out of the way. Let's talk about how we can use this extra capacity. Like you mentioned earlier, so many cores, so many threads. What do you do with, how do you make best use of it? Well, with this added capacity, some of the things you could do is just have larger data. So for example, if you have a database that's tracking 1,000 employees, you could have a bigger database that tracks 1,500 employees. So you could just basically have larger data. Another option is you can use it as a TCO balancing tool. So you have performance. You could have the same capacity for a lower TCO, or you can increase the capacity a little and balance the TCO that way. Oh, we're running low on time. I'll try to speed this up. Okay, and another way you could use this is if you have a virtualized system and you have a bunch of VMs with bigger capacity, you can run more VMs, or you can have bigger VMs.
So one quick question between the previous slide and this slide when it comes to virtualized systems. As I'm getting the telemetry data from VTune, is that upon the virtualization provider to pass that information on to the host, or is that only available at that virtualization extraction layer? So can I tune, if I'm consuming this as a cloud instance, can I get that VTune data to tune my workloads for that target type of system?
I think that's the eventual goal. I think for right now it's just at the system level, but that's the goal.
Okay.
Okay, with our negative time here, I just wanted to go through the example of the virtualization and how you can have more VMs with this larger capacity, how you can take advantage of it. So there's two lines on here. The red one is an experiment we ran with Redis. It's an open source database and running a benchmark that does a read-write mix. So it's got a VM size of 90 gig, which is a pretty generous sized VM. And in each VM, we're running one instance of Redis. So as we increase the capacity, we're able to instantiate more VMs. That makes more sense. You've got more space, you can instantiate these 90 gig VMs. and all the way up to 6 terabyte, where we can instantiate 56 VMs. Now, what does this mean for performance? Well,
This
we
is
are
running in memory mode?
This is all in memory mode, yep. So we're running a max throughput scenario, and we're measuring the SLA. And in all cases, all the way up to 56 at the top there, we're getting less than 1 millisecond, which was the SLA that we were shooting for. So this is a perfect example of up to 8x VM density increase because we've increased the memory footprint size. The blue line is very similar.
What's the DRAM to Optane ratio here?
For this one, it's the DRAM is 32 gig, and the Optane goes up to 6 terabyte. Oh, sorry, 32 gig times 12. So
That's okay.
yeah. Okay. The blue line is a similar experiment, but with a smaller VM size, 45 gig, and you get a similar scaling all the way up to the dotted line. And what happens at the dotted line? That's where we're at 56 VMs. Beyond that, something other than memory capacity also starts to come into play. And that's beyond 56 VMs, we're starting to put more than 1 VM on a core. Once you do that, then the core, you start trading off the core versus memory capacity. It still does continue to scale, just not at the perfect linear rate. But this is an example of how we've increased memory capacity to the point where it stopped being the bottleneck.
So, did you experience it something like, with the storage, with the VMs, we had the blender effect. Okay, so all the workloads from the VMs mixed together created a huge blob that it was hard to identify from the storage perspective, and it all those cache misses at the end. Okay. Did you see something similar also with the memory in this case?
Yeah, the more VMs you have, the wider the variance in read-to-write ratio, the wider the blender mode and on.
Yeah, so I don't know even how to call it in memory, but actually you start doing different access patterns, and
so you're talking about how that varies your latency?
Yeah.
Yeah, so obviously we ran these multiple times, and obviously, especially in the blue line, we saw the higher latency, but it wasn't just because of the memory. It was a combination.
Yeah, all the
of
system
things.
was
right.
A lot of,
Right, but for these experiments, we ran.
The other thing is, this is really good in terms of efficiency of the overall system, but actually you put like, as you said, 60 Redis machine in a single server, which is a failure domain that is massive. Meaning, it's good if you have thousands of servers like this. So if I am the Facebook of this world, I like it because, if I lose 60 VMs is okay. But if I have 3 servers with 60 machines each, it's a huge.
It's a benchmark.
No, yeah. I mean, so putting all this RAM and all these cores in a single rack unit, for example, meaning it's not for everybody. If you have just 10 servers.
Probably not for anybody. It's really to determine the kinds of workloads that.
I'm telling. So I'm trying to, to understand where we can put this kind of technology. So even a.
Well, if you're a cloud vendor, you have this. I'm sorry. Go ahead.
No, yes.
So that's a good point, right? A hyperscaler might possibly.
Yes, if you are an hyperscaler, it's the best thing that you can have. If you are a mid-sized company, then it's too much.
Yes,
It's just too much. Maybe they have smaller CPUs to sell, but and
Besides, with all this big data, you can just imagine databases will probably grow in the future if you've got this much capacity. And there is the other 98% of the data in the world we need to process, so this is a good place to do it. Okay, we are over time. Should I continue?
Yes.
Okay, great. So now we're switching gears. We're going to app direct mode. This is the one where the application, there's lots of things you can do with the application to make a difference. And to really understand app direct mode, I want to go through a quick transaction flow again. First, starting in the middle of the page, traditional read page fault. So this is with the disk. So let's say you have a page fault. It's not in memory. You need to go fetch from the SSD. So first, software runs. There's some layers of software in the kernel and other things. The software runs and then invokes the protocol to transfer 4K from the disk into memory, because everything's on a 4K boundary in disks, in drives. And then finally, you reissue the command and you get your read back. So it's very expensive to have a page fault where something's not in memory and you have to go fetch it. In comparison with AppDirect, it's just a simple 64-byte read, and it comes back as one cache line, and you're done. So much simpler. It avoids all the software overhead and the 4K transfer. And even while you're doing this, other cores can still access DRAM normally, even on the same channel. We already looked at the SNIA programming model. I'm going to talk mostly about the right side of the page where an application can make changes to optimize for AppDirect. Quick refresher, with AppDirect, you have a certain portion of memory that's DRAM, and then you have a certain portion of memory that's AppDirect, and it's persistent. There's many different ways that an application can take advantage of this persistent memory space. One of them is to move content that was in DRAM over to this AppDirect space, and it enables larger data structures or TCO balance, that type of thing. So one way to do that would be to take your entire data and move it all into AppDirect. Probably a little bit more efficient way to do it is to move some of the data, let's say of an in-memory database, into persistent AppDirect space and leave most of the actively accessed data in DRAM. And here's a SAP HANA example. This is actually a foil from SAP HANA. And this is what Mohammed was talking about a little bit earlier, where we've taken the main store and moved that to persistent memory. And this is the largest part of the data. And so you move it to the persistent memory, you get a much better TCO. You have the possibility of a much larger database now than you did before. And if you compare with the way it may have been traditionally done with more sockets, this is a much easier way to get that larger capacity with AppDirect. Now, what remains in DRAM is all the active structures. So like the working memory, and then there's that little box there that says delta. That's where all the changes go into this delta. And then periodically there will be a delta merge function where the data that's been modified will move into the main and become persistent. And SAP keeps track of all this. So that's how we guarantee persistence even if something explodes.
So is this based on workload type? So is this across the board from analytic workloads and transactional workloads, or is this mainly for analytic workloads?
This is anything with SAP.
Okay.
So what this does for us is with the data in persistent memory, on a reboot, you never have to load from the disk again. The table's already there. And I've already talked about the increased capacity and the better TCO. Okay, a different way to use AppDirect is to take data that was previously in the disk and accelerate the performance by moving it into AppDirect. And we looked at the performance characteristics of the module, and so there is a lot of potential for performance benefit doing this. One way to do this is to move the data that was in a disk and move it into persistent memory and then re-architect the application so that it's taking advantage of byte addressable instead of blocks. An example of that is Cassandra actually has been rewritten to skip a whole bunch of steps in the software flow and directly just access data and back out again. Another way that AppDirect can be used is as a cache. I've got an example coming up on that. And again, just like we were talking about with the memory mode, you can do multiple modules in parallel with no software change, and gives you higher bandwidth just like DRAM would have done. And Mohammed's already talked about storage over AppDirect, so I'll skip that. Here's an example of another workload that's been modified to take advantage of this direct access. And to really understand this, we'll start on the left. This is an example of Redis, now in AppDirect mode. Well, actually, the one on the left is Redis just running on a normal DRAM system. And all the keys and values are in DRAM. And then in parallel, there's an append operation going into a log file, which is going to disk. Now, traditionally, writing the AOF file or the log file is a system bottleneck. It's one of the slowest parts of the system. And so using AppDirect solves a whole bunch of problems all at once. The picture on the right, we've moved the values from DDR into persistent memory. This gives you larger capacity and better TCO. But the other thing that it does is, since you've got the values now persistent, you don't need to log the entire value. And in fact, all that needs to go into storage is the pointer to the log. So much smaller than the actual value. With that move, with not having to write the log to the drive with all the protocol overhead, we see a good performance advantage, and at the same time, you get better TCO because you've reduced the amount of DRAM needed. As promised, here's an example of using the AppDirect as a cache. This is a Spark SQL example. And over on the right, you see a picture there. There's the Spark computing task, and normally it goes to storage to fetch. And so this just adds the AppDirect as a cache. And this happens to work as an I/O cache. And what we've run here is a bunch of I/O-intensive workloads from a decision support benchmark, and you get a tremendous performance boost, which we've talked about in other forums, but this is how it works. Okay, so just to quickly wrap it up, this is a new way to manage data flows. As we've talked about before, it's Optane technology, it's full system on a module, it's every piece of the platform, software, hardware, firmware, silicon, every piece. And as Mohammed mentioned, this really was made possible by the scale and capabilities of Intel.